Question 1. Which option correctly describes how current flows in circuits with multiple resistors? Does the current through resistors in series always equal? Is the current through resistors in parallel always equal? Is the resistance of resistors in series always equal? Or is the resistance of resistors in parallel always equal? Now, based on what we've learned about resistance, we should know that the resistance of a particular resistor does not depend on how that resistor is wired into the circuit. The resistance of a resistor depends only on what the resistor is made of and its shape and so on, right? It doesn't depend on how it's wired into the circuit. The other two options are to do with the current through the resistors. So is the current through resistors the same when they're in series or when they're in parallel? Well, if the resistors are in parallel, we'll get the current splitting up when it reaches the branch of the parallel circuits. It turns out that if the resistances of each branch are different, the current through each branch will be different as well. The correct answer then must be A, that's the only one left. Now, if we have two resistors in series with each other, that means the same number of electrons will pass through each one in the same period of time, which means that A must be correct. The current through resistors in series is always equal because the amount of charge passing through them per unit time will be the same. Question 2, Part A. In one set of Christmas lights, when one bulb burns out, all of the bulbs stop working. Are the bulbs in series or in parallel with each other? Now, when a resistor that's in series with other resistor breaks, no current can flow through the broken resistor. And if no current can flow through one resistor, and it's in series with others, then no current flows through any of them, because the current through each resistor in series must be equal. So our answer is that they must be connected in series. When one bulb breaks, all the other ones stop working as well, because the circuit is broken. Question 2, Part B. In a different set of Christmas lights, when one bulb burns out, the other bulbs keep working. Are the bulbs in series or in parallel with each other? Now, we know that it can't be in series, because in series, if one bulb stops working, then the others have to stop. So the answer must be in parallel. And we can see that if we build a parallel circuit, something like this, and one of the branches of the parallel circuit breaks, the rest of the wires still form a perfectly good parallel circuit, right? So our answer is they must be connected in parallel, because reducing the current to zero in one bulb does not reduce the current in all the other bulbs. Question 3. Copy the circuit diagram, placing an ammeter in series with the resistor and a voltmeter in parallel with the resistor-ammeter combination. So we can't just straight away put the voltmeter in parallel like this. If we do that, then it would be in parallel with the resistor, but it would not be in parallel with the resistor-ammeter combination, right? So what we should do first is place the ammeter in series with the resistor, which will look something like this. So you can see that the ammeter is lined up with the resistor. They're together like links in a chain, which means they're in series. Then when we put the voltmeter in parallel with the combination of the two, the circuit might look something like this. So you can see that because it's in parallel, we have two branches that current can pass through in the circuit, right? Although here I've drawn the direction of the electrons rather than the direction of the conventional current. Although the electrons are what really causes the moving charges and the electricity, remember that in circuit diagrams, we always draw current going from the positive terminal to the negative terminal, even though that's the opposite of the direction in which the electrons travel. Question 4. Two identical resistors are placed in a circuit. How does the current through them differ if they're placed in series with each other? So in this case, we have two resistors and they're in series with each other. Now, when current flows through them, we're going to have the same number of electrons passing through each one, right? Because there's going to be a constant current drawn from the power source. So if they're placed in series with each other, the current through them will have to be equal. The same current will flow through all devices that are in series with each other, so the current through each will be equal. Now here's the second part, and it might require a bit more thinking. How will the current through them differ if they are placed in parallel with each other? So in this case, if there's our power source, the resistors look something like this, right? Now these two have identical resistance. So when the electric current splits up at the branch, what proportion of the current will go into each branch? Well, it probably has something to do with how much resistance the resistors have, right? But we know here that the two resistors are identical. That means that the two branches of the circuit are identical. And that means that when the current splits up to go into the two branches, it splits up in equal parts. So in this case, the electric current will branch out, but it will branch out identically to both branches because each branch has the resistance of the single resistor. And this means that the current through each resistor will once again be the same, although we can't tell at this point whether it will be larger or smaller than the current through the resistors in series. Question 5. Two resistors are placed in a circuit. The resistance of one resistor is very large, and the resistance of the other is very small. How does the current through them differ if they are placed in series with each other? Now this one should be fairly easy to answer because we know how current behaves when it goes through resistors that are in series. The same current flows through all devices that are in series with each other, so the current through each will be equal. Part B asks, what happens if they are placed in parallel with each other? So for this we might need a bit of a hypothetical, so stay with me. We have a power source, right? Now we have two resistors. One resistance is very small, and so to represent a resistor with a very, very small resistance, I'm simply going to draw an empty wire, because an empty wire has a very low resistance. In order to represent something with a very high resistance, I'm going to leave an open circuit, because air has a very high resistance when it's dry and at low temperature. So how will current flow through here? We'll get it drawn out of the power source and coming back in. It won't be able to flow through the top part of the circuit because the circuit's open, right? So there's going to be very little, if all, electric current that's able to jump that gap. If, on the other hand, we look at the other branch of the circuit, we have next to no resistance because we have a wire with no resistors. So there's going to be a large current through that wire. And this helps us to answer part B. So the empty wire, that is the wire with no resistors on it, has a very large current, and the other wire, the one that has air in it, because it has a very large resistance, has a very low current, right? So how do we answer this question? We can say that when electric current reaches a branch, it is divided into two parts. A larger current passes through the small resistance, and a small current passes through the large resistance. We'll be learning exactly how the proportion of each current varies later on when we learn about parallel circuits. For now, we've finished the questions, so this is the end of the section. We've learned about the structure of circuits and how resistors can be placed in series or in parallel with each other, or even in series or in parallel with a combination of other resistors.